Every computer has a brain, but there are different kinds of brains. CPUs, GPUs, TPUs, DPUs, and even QPUs, each built for different purposes. From your phone to clouds to quantum labs, these processors shape the future. In this video, we'll explain what they do, how they differ, and where they're heading. Think of the CPU as the manager of a company. It handles the OS, your apps, logic, and 1-0. Consumer CPUs typically have 4 to 16 cores. Servers have many more. Great at sequential tasks, problems step by step. Examples: opening Chrome, editing docs, running game logic. But give it millions of repetitive tasks and it slows down, not optimized for massive parallelism. That's where other processors come in, like the GPU. Versatile and essential but limited when parallel work dominates. Now let's turn to the GPU, or Graphics Processing Unit. As the name implies, its story begins with visuals. Early 3D video games demanded a new kind of power to calculate the color, light, and position for millions of on-screen pixels, all in a fraction of a second. This need for massive repetitive calculation gave birth to the GPU. A GPU's design is fundamentally different from a CPU's. While a CPU has a few powerful cores like surgeons performing unique, complex operations, a GPU is an army. It has thousands of smaller, simpler cores working in lockstep. Imagine a factory where thousands of workers perform the exact same task simultaneously. This is the essence of parallel processing, a concept known as single instruction, multiple data. This architecture is perfect for graphics, where the same calculations apply to millions of pixels. But researchers soon realized the math behind graphics, primarily matrix multiplications, was the same math at the heart of scientific computing, and this discovery, known as GPGPU, or general-purpose computing on GPUs, repurposed gaming hardware for world-changing research, long before dedicated chips existed. This versatility unlocked a new era. Today, GPUs are the workhorses of the revolution, training the large language models and image recognition systems reshaping our world. They're indispensable in science, modeling everything from weather patterns and protein folding for drug discovery to the collision of black holes. Their knack for repetitive hashing also made them the engine for mining cryptocurrencies. It's important to distinguish between consumer and data center GPUs. Consumer cards like NVIDIA's RTX series are optimized for gaming with features like real-time ray tracing. Data center behemoths like the A100 or H100 are pure computational accelerators. Stripped of video outputs, they are packed with immense memory and power, designed to run 24/7 in server racks, pushing the boundaries of and science. But the GPU's strength is also its weakness. Its architecture thrives on repetition but falters with complex decision-making or branching logic. If a task involves many if-this, then-that conditions, the GPU's parallel army stalls as different. Groups of cores try to follow different paths. In these scenarios, the CPU's versatile, sequential approach remains superior. The GPU's success in accelerating paved the way for even greater specialization. As demands grew, it became clear a chip designed for neural network math could be more efficient. For these specific workloads, a new challenger emerged, the TPU. GPUs brought massive parallel throughput, but TPUs would optimize the math even further. While GPUs proved powerful for general Google saw an opportunity for greater specialization. To run their massive deep learning workloads with maximum efficiency, they built a custom chip from the ground up, the Tensor Processing Unit, or TPU. The clue is in the name, tensor. Tensors are the fundamental data structures of multi-dimensional arrays of numbers. TPUs are optimized for the mathematical operations on these tensors, which form the very backbone of deep learning. Their key innovation is the systolic array, a grid of processors that acts like a synchronized assembly line for math. Data flows through the chip in waves, making it incredibly efficient for the massive matrix multiplications in This specialization is why TPUs can outperform GPUs on speed and power efficiency. A GPU is a versatile Swiss Army knife. A TPU is an ASIC and application-specific integrated circuit. It's a scalpel designed to do one job exceptionally well. This performance is essential for training today's colossal models. That's where Google Cloud's TPU pods come in. They are supercomputers of thousands of TPUs linked together, functioning as a single, massive accelerator for the most demanding training tasks. But TPUs aren't just for the cloud. Google also scaled the technology down into edge TPUs, tiny, low-power versions that bring AI inference directly to devices like smart cameras and factory sensors. From data center titans to tiny edge devices, TPUs demonstrate the power of specialized hardware in the age of AI. But processing data is only half the battle. What about moving it? Next, we'll look at chips designed to offload data handling, so CPUs and GPUs can focus on compute DPUs. DPUs offload data-centric tasks from CPUs. Networking, storage, encryption. Think of a traffic cop managing the data highway, also called smart NICs. Example, NVIDIA Bluefield DPU, crucial for cloud, hyperscale data centers, and AI pipelines. They free CPU cycles for core work. And then there's an entirely different paradigm, quantum processors. QPUs use qubits instead of bits, exploiting superposition and entanglement. Qubits can represent many states simultaneously, enabling massive parallelism of a different kind. Entanglement links qubits, so their states correlate instantly across the system. Potential: cryptography breakthroughs, drug discovery, optimization, and complex simulations. But qubits are fragile and error-prone, needing extreme conditions like near absolute zero. Examples: IBM Quantum, Google Sycamore, D-Wave, still experimental but rapidly evolving. So, let's bring all 5 processors onto one stage for a final showdown. First, the CPU, the central processing unit. Think of it as the master chef of your computer, a brilliant generalist with a few powerful cores. It runs your operating system and apps, excelling at sequential tasks with low latency. It's the indispensable brain of every PC. Next, the GPU, or graphics processing unit. If the CPU is a master chef, the GPU is an army of sous chefs. Its architecture has thousands of smaller cores, creating massive parallelism. This is perfect for rendering 3D graphics and made it the hero of the AI revolution, accelerating deep learning models. Now for the specialist, the TPU, or tensor processing unit, a purpose-built AI accelerator. It's like a hyper-efficient factory, assembly line designed for one thing: the matrix multiplication at the heart of neural networks. This singular focus gives it incredible speed and power efficiency, making it the secret sauce behind Google's AI services. Let's turn to the unsung hero of the data center, the DPU, or data processing unit. As data centers grew, CPUs became overwhelmed managing data flow. The DPU acts as a logistics manager, offloading infrastructure tasks like networking, storage, and security. This frees up the CPU to focus on computation, making the entire system faster and more efficient. Finally, the QPU, the quantum processing unit. This isn't just a faster chip. It's a new way of computing. Using quantum principles, QPUs use qubits instead of bits. They aren't meant to replace your CPU, but to solve problems impossible for any classical computer, like discovering new medicines or designing novel materials. It's a revolutionary tool for science. So, to recap, the CPU is the versatile brain, the GPU is the parallel powerhouse, the TPU is the AI specialist, the DPU is the data center's efficiency expert, and the QPU is the quantum pioneer aiming to solve the unsolvable. The key takeaway is that there's no single best processor. The future of computing is heterogeneous. The era of one chip fits all is over. It's about choosing the right combination of tools for the job to build faster, smarter, and more efficient systems. As these technologies evolve, I want to ask you, which processor will have the biggest impact in the next decade? The AI power of the TPU, the quantum potential of the QPU, or the classic CPU and GPU partnership? Let me know in the comments. And if you enjoyed this journey, please like this video and subscribe for more. Sharing this video with a tech-passionate friend would also mean the world to us. It's the best way to help the channel grow. Thanks for your time and curiosity. We'll see you in the next one.